Excel Solver is a tool that tries to find optimal solutions for all kinds of decision problems. It basically determines the minimum and maximum of cells by changing the value of other cells. Excel has Solver by default, but you have to add it as an add-in in the Data tab. First, we will show you how to do this. After that, we dive into its functionality, and we will see that it isn't too bad to work with once you understand the basics. So to load the Solver add-in in Excel, you go to File, Options, Add-ins. There you see Manage Excel Add-ins. You click on Go, and here you can highlight the Solver add-in and press OK. Now to find the Solver tool, you go to the Data tab, and there you can find Solver in the ribbon. To show how exactly you can use it, we will go through some examples. Our first example is a magic square solution. This is a 3x3 square consisting of the number 1 up to 9 that satisfy a few rules. First, all numbers 1 up to 9 should be present in the square. Second, the sum of all rows should be 15. Third, the sum of all columns should be 15. And finally, the sum of the up diagonal and down diagonal elements should be 15 as well. In the blue cells, we calculate the sum of the rows, the columns, and the diagonals. Let's fill in some random values to show this. Let's choose numbers from 1 to 9. It does not matter which cell you select at this point. You navigate to the Data tab and click on the Solver tool. The first element to enter is the objective. Here we do not have a specific objective. We are not interested in minimizing or maximizing a certain cell, nor in setting a certain cell equal to a specific value. So in this case, we do not enter anything here. Next, we have to indicate in which cells we would like the value to be changed. Those are all the elements in the square, so we select them all as we would normally select a group of cells. So in our case, B5 to D7. Beneath the changing variable cells, we have the potential constraints we can add. In this case, we want that the sum of each row, each column, and each diagonal is 15. The square elements should all be different, and it should be integer values. To implement these constraints, we click on Add. Then a window pops up where we can enter our constraint. First, we make sure all row sums are 15. To do that, we select the cells containing the row sums as cell reference. In our case, these are E5 to E7. For the second option, we choose the equal sign. As constraint, we fill in 15. Then we click OK and see that the constraint is added to the constraint box. To add the next constraint, we again click on Add and then enter the following constraint. We now tell Solver that all columns should be 15. So first we enter the cells containing the column cells B8 to D8, then the equal sign, and finally, again, 15. Remark that you can simply add the next constraint without returning to the main Solver menu by immediately clicking Add instead of OK. So let's click Add and implement the diagonal sum constraint. In the cell reference, we enter the cells containing the diagonal sums. Then we enter the equal sign and finally the 15 in the constraint box. At the moment, we added 3 constraints. Now, we still have 2 constraints on the changing value to implement. The fact that it should be all integers and the fact that the values should be all different. Let's start with the first one. Again, we click on Add. For the next constraint, as cell reference, we select all elements of our square. B5 to D7. In the next box, we change the value to int. As you can see, the word integer appears in the constraint box. This is okay, so now we go to the last constraint to enter. We click on Add. We select the changing cells B5, D7, again as cell reference. Now we choose diff in the second box. We see all different appear in the constraint box. This was the last constraint, so we click OK. In total, we have 5 constraints. When all constraints are implemented, there are still 2 more functionalities to consider. First, you can choose to make unconstrained variables non-negative. The interpretation of this functionality is straightforward. If you highlight the box, no negative values are allowed for the changing variables. And if you do not highlight the box, it's the other way around. Finally, you have 3 options you can choose as solving method: GRG nonlinear, simplex LP, and evolutionary. Each has its own pros and cons. I will explain the difference between these 3 options after solving the magic square. For now, we change the solving method to simplex LP. Click on Solve so that Excel can work its magic. We receive the following result. We see that Solver found an integer solution within tolerance and that all constraints are satisfied. So we know the problem is solved. As we see in the sum boxes, all sums are equal 15. The elements are all integers and they are all different. Now to explain the differences between the solving methods, we switch to a different sheet in our Excel workbook. I am afraid that this next bit does include a bit of mathematics. Here you can see 4 types of objective functions representing a certain problem to solve. The first function you see is a linear one. This can be solved with all 3 methods. However, simplex LP is especially made for these types of problems, and it is the fastest and most efficient to find a solution. The second function you see is a nonlinear function with only one optimum. This can be solved by the GRG nonlinear and evolutionary methods. Here the GRG nonlinear method will be the fastest and most efficient way to come to a solution. The third function you see is a smooth nonlinear function with 2 optima. In theory, this can be solved by either the GRG nonlinear or evolutionary solving method. However, in practice, it is better to choose the evolutionary method. This will take more time than the GRG nonlinear method, but you will be sure to have the global optimum, which is the one on the left, and not only a local optimum, which is the one on the right. The fact that GRG nonlinear might fail to give the global optimum is because the method depends on the initial conditions the method chooses. If the initial conditions are chosen as on the graph, then the method is more likely to return only the local optimum as a final solution, as this one is the closest. The last function you see on this sheet is a non-smooth, non-linear function with 2 optima. Because of its lack of smoothness, this problem can only be solved by the evolutionary solving method. Now we have seen when to use which solving method, we understand our example of the magic square. In this example, the objective function is linear in each changing variable, and we have a smooth function as there are no discontinuities by, for example, an if statement. Hence we can use the simplex LP solving method. Now we can move to the next example. Here we would like to construct something. Let's call it construction X as written at the top of the table. We can construct this by using wood, brick, concrete or metal. Each material has its own price and its own solidity, which limits the number of pieces you can use of it in the entire construction and has an impact on how much you use of something to replace another material. Let's consider wood as an example. We see in the table that one piece of wood costs 100 euros. You cannot use more than 2,000 pieces in the entire construction, and one piece of metal can be replaced by 2 pieces of wood as the replacement factor is 0.5. If you would build a construction of only metal, one requires 5,000 pieces to finish. With this information, we can create a potential solution. At the bottom of the left table, you see a cell containing the total price of the construction, which takes the product of the amounts and prices and then sums it. Below that cell, you can see the amount of pieces required, which should always be 5,000. If you take the replacement factor into account, therefore this cell contains the sum product of the amounts and the replacement factors. So a potential solution could be to take 1,000 pieces of wood, 1,000 pieces of brick, 1,000 pieces of concrete and 3,000 pieces of metal. As you can see, this amount of pieces takes the replacement factor into account, equal exactly 5,000 as required. If we choose this composition for construction, we see that the cost is 1 million. Now we go to the solver and check if a cheaper solution is possible. We go to data and click on solver. In the objective, we indicate that we would like to minimize the total cost of the construction. So we enter cell C21 and highlight min. Next, we change the range of our changing variable cells. These are the cells next to wood, brick, concrete, and metal, so C17 to C20 for our case. Then we add all the constraints. You have constraints on the amount of pieces per material and the total amount taking the replacement factor into account. We click on Add and start with the first constraint on the amount of wood. The amount in the left table should be less than or equal to the max amount in the right table. Then we add the same constraint for brick, concrete and metal. Finally, we add the constraint that the total amount should be equal to 5,000. So we take C22 as cell reference, we choose the equal sign and type 5,000 in the constraint box. Keeping in mind that brick and concrete don't count as 1 when taking the replacement factor into consideration, we click on OK and all constraints are added. Here we again have a linear function in all our variables, so we choose the simplex LP method and click on solve. We click on OK to keep the solved solution and see that the cost is reduced to 903,750 euros. Let's move to the final example. Here we show how to solve a mathematical equation. We want to find x so that e to the power x equals minus 3x. This is the same as setting e to the power x plus 3x equal to 0. This is what we will try to find using the solver. As you can see in the cell next to fx, we have written the formula we would like to set equal to 0 by changing the x value in the cell above. Now we go to Data, Solver, and enter cell C30 in the objective box. We want to set this equal to 0, so we highlight the value of and fill in 0 in the box next to it. And this we would like to do by changing the x value in cell C29. Don't forget to allow for negative solutions, so make sure that the Make Unconstrained Variables Non-Negative line is not highlighted. As the objective function is smooth and not nonlinear, we choose GRG nonlinear to solve. We click on solve, press OK, and found that the solution is about minus 0.26. This concludes our complete Excel solver tutorial. I hope you found some value in this guide and are ready to use the feature yourself. Comments or feedback are always welcome, and I'll see you in the next tutorial.